There is a piece of equipment right now hurtling through deep space that is going to do something no instrument in history has ever done. It is going to scan the inside of an alien ocean, not from orbit, not with a telescope, with a radar beam that punches through miles of ice and reads what is underneath. And the test it just ran, bouncing signals off a planet 60 million kilometers away, came back with data so clean and so precise that the scientist in charge of the instrument said out loud that they got everything out of it that they dreamed. Subscribe right now before this video goes another second, because everything that has happened with Europa Clipper in the past 12 months is building toward a single answer. And the new research that dropped in January this year completely changed what scientists think they're going to find when the spacecraft finally arrives. Europa Clipper launched on October 14, 2024, from Kennedy Space Center in Florida. It is NASA's largest interplanetary spacecraft ever built. The solar arrays alone are the size of a basketball court, designed to collect what little sunlight reaches Jupiter, which is 5 times farther from the sun than Earth. The spacecraft carries 9 science instruments. It will travel 1.8 billion miles to reach Jupiter in April 2030. Then it will begin conducting 49 close flybys of Jupiter's moon, Europa, passing as close as 16 miles above the surface on some passes, with every single instrument running simultaneously on every pass. The moon it is going to study sits right there in our own solar system, orbiting Jupiter, and it may contain more liquid water than every ocean, lake, river, and glacier on Earth combined. Not might have contained it once, may contain it right now. Beneath an icy crust that covers the entire surface of the moon, scientists believe there is a global ocean of salt water that has been liquid for potentially billions of years, kept warm not by sunlight but by tidal forces. Jupiter is so massive and its gravitational pull is so powerful that it squeezes and stretches Europa as the moon orbits, generating heat from the friction of that constant internal flexing, the same way a piece of metal gets warm when you bend it back and forth repeatedly. That process, called tidal heating, is what keeps the water liquid in a place where the surface temperature is around minus 220 degrees Fahrenheit. The surface itself is one of the most visually striking objects in the solar system. It is covered in reddish-brown streaks and cracks that crisscross each other in patterns that look like someone wrapped the moon in a ball of string. Those lines are fractures in the ice shell, formed as the tidal flexing cracks the surface and allows material from below to well up and refreeze. The reddish color along the fractures comes from salts and other chemicals from the ocean beneath being deposited at the surface. When scientists look at those red streaks, they are looking at ocean material that has reached the outside. The ocean is communicating with the surface. Now, here's what happened in March 2025 that changed everything about what scientists know the spacecraft can actually do. As Europa Clipper flew past Mars on a gravity assist maneuver, mission controllers activated the spacecraft's most critical instrument. The instrument is called REASON, which stands for Radar for Europa Assessment and Sounding Ocean to Near Surface. REASON is an ice-penetrating radar that will be used to map the thickness of Europa's ice shell and search for liquid water beneath the surface. It had been impossible to fully test this instrument on Earth before launch, because doing so would have required a chamber large enough to simulate the distance that radar signals travel in space. The Mars flyby was the first opportunity to test the radar in its complete operational form in space. The instrument was activated for approximately 40 minutes as Europa Clipper descended from an altitude of about 3,100 miles to 550 miles above Mars. REASON directed its very high-frequency radar waves toward the Martian surface and listened for the echoes bouncing back. The 40-minute test produced approximately 60 gigabytes of raw data and generated a radargram spanning roughly 900 kilometers of equatorial Martian terrain. When engineers compared the results with pre-flight models, they found strong agreement. Don Blankenship, the principal investigator of the REASON instrument, said, "We got everything out of the flyby that we dreamed." Trina Ray, the deputy science manager for Europa Clipper at JPL, described the reaction of the team when they first saw the data coming back as scientists, saying out loud, "Oh, look at this. Oh, look at that." The instrument that is going to search for liquid water inside an alien moon just proved it works exactly as designed, in actual deep space conditions, against a real planetary surface. That test removed the last major uncertainty about whether Europa Clipper will be capable of doing what it was built to do. At Europa, the REASON instrument will operate as close as 16 miles from the moon's surface, far closer than the 550 miles at which it was tested at Mars. The closer distance means the signal will be stronger and the resolution will be higher. The instrument carries 2 pairs of slender antennas each, stretching to 17.6 meters in length. When those antennas fire their radar pulses toward Europa's surface, the waves will pass through the ice shell and reflect back from any interfaces within it, including the boundary between the bottom of the ice and the top of the liquid ocean, and any pockets of water trapped within the ice shell itself. The returning echoes will be processed to produce maps of what is inside a world that no spacecraft has ever penetrated. But while the radar test was demonstrating that the spacecraft works, scientists on the ground were wrestling with a problem that has sat at the center of the Europa habitability question for decades. And in January 2026, a pair of researchers at Washington State University published a study that may have just answered it. The problem is this: Jupiter constantly bombards Europa with intense radiation. That radiation interacts with the salts and chemicals on Europa's surface ice to create oxidants and other chemical compounds that could serve as nutrients for any life in the ocean below. This is significant because life needs energy sources other than sunlight when it is buried under miles of ice with no access to the sun. Chemical nutrients created at the surface by radiation could serve that purpose, but they are at the surface. The ocean is underneath 30 kilometers of ice. And for decades, nobody had a convincing mechanism for how those nutrients could travel down through the ice shell to reach the ocean that needs them. The new study from Washington State University geophysicists offers a direct solution. Salty, nutrient-rich surface ice on Europa can become heavy enough to break free and sink through the icy shell, delivering essential ingredients to the ocean below. The process is fast, repeatable, and works under a wide range of conditions. The mechanism works because certain areas of Europa's surface are rich in salts, remnants of ocean material that has come up through the fractures and refrozen at the surface. The addition of salts to ice makes it denser than the surrounding purer ice. Salty ice is also significantly more ductile and weak than pure ice, with this weakness increasing under repeated stress. The team used computer modeling to test whether this dense, weak, salty ice could detach from the upper surface layer and sink through the 30-kilometer ice shell. They found that nutrient-rich surface ice can sink all the way to the base of the ice shell for almost any salt content, as long as there is at least a small amount of weakening in the surface ice. According to estimates from the study, a single sinking event of salt-laden ice roughly 15 kilometers in scale would significantly contribute oxygen to the ocean. The process is analogous to crustal delamination on Earth, where dense crustal material sinks into the mantle below it. On Europa, dense salty ice sinks through the softer interior ice layers to the ocean base, delivering its chemical cargo along the way. Think about what this means. The surface of Europa is being hit by Jupiter's radiation, which creates chemical nutrients in the ice. That radiation-enriched salty ice is denser than the pure ice around it. Because of that density difference, it breaks away and slowly sinks, all the way down through the ice shell, and delivers those nutrients directly to the ocean. The ocean is not sealed off from the surface chemistry after all. There is a conveyor belt. The ice itself is the delivery mechanism. The findings directly align with the primary goals of Europa Clipper. The mission aims to study Europa's chemistry, its ice shell, and its habitability, and specifically to obtain evidence of salt-laden sinking ice. The researchers designed their study in part as a hypothesis that the Clipper mission can directly test. When Reason fires its radar into the ice shell and maps what is inside, one of the things it will be looking for is evidence of this sinking process, the signatures of dense material moving downward through layers that have different density and composition. But this same week that the sinking ice study came out, another study published in July 2026 added a complication that scientists are still working through. Scientists had hoped that water from Europa's deep ocean might rise through cracks in the ice and form shallow reservoirs just below the surface that future spacecraft could more easily study. New computer simulations suggest that journey is unlikely. Turbulent water rising through fractures would rapidly lose heat, form ice crystals, and clog the fractures, sometimes within hours. This finding does not eliminate the possibility of life in Europa's ocean. It changes where scientists expect to find evidence of that life. If water from the deep ocean cannot easily rise into shallow subsurface reservoirs, then the surface features that appear to show ocean material at the surface are more likely explained by the salty ice process going downward rather than deep ocean water coming upward. The shallow water lenses that scientists had hoped to detect just below the surface, and that some had thought would be easier targets for future missions than the deep ocean itself, may not be supplied by the deep ocean after all. What the combination of these two studies means is that Europa's habitability story is more complicated than the simple picture of an ocean sitting under ice waiting to be found. The sinking ice creates a pathway for nutrients to reach the ocean from above. The lack of upwelling means the deep ocean is more isolated from the surface than previously hoped. The ocean exists and may be habitable, but accessing evidence of whether it actually hosts life is going to require exactly the kind of deep, penetrating radar that Europa Clipper's Reason instrument is designed to provide. The spacecraft is currently about 280 million miles from Earth, still years away from Jupiter. It will receive another gravity assist when it swings past Earth in December 2026, which will give it enough velocity to reach Jupiter in April 2030. After arriving at Jupiter, it will begin its orbit and start the flyby sequence. With all 9 instruments running on every single pass, accumulating data across 49 separate close approaches before the mission concludes. The 9 instruments collectively cover an extraordinary range of measurement capabilities,